Most people are intrigued by the heliotropic nature of sunflower.
But what is not always clear is the mechanism behind heliotropism. For the sunflower, these mechanisms are heat differentiation, fluid dynamics, and physical pressure.
This chain of events begins at the pulvinus, the area where the flower meets the stem.
Part of the pulvinus shaded by flowers stays cool and causes a heat difference between it and the other side. This heat difference triggers evaporation, causing a concentration gradient between the hot and the cool side.
This difference in concentration triggers osmosis, producing a mechanical effect of fluid movement, which brings the plant into equilibrium.
When the pulvinus absorbs liquid, it expands. This expansion produces another mechanical effect, physical pressure. An expanded pulvinus puts physical pressure on the flower, pushing it toward the sun.
These mechanical effects of heat differentiation, fluid movement, and physical pressure becomes the foundation for our models.
This model replicates the sunflower's constant response to its external environment without direct contact. A series of magnets on the inside of two discs repel one another to prolong the spin.
For this model, we will add additional water to the cup at the top of the model. The water will flow down tube number 1 into the bottom bottle. As the water level rises, air pressure increases, and air is forced through tube number 2 up to the top bottle. The increased air in the top of this bottle forces the water downward and out of tube number 3 into the cup at the top, thus causing a flow of air and water until equilibrium is reached. The transfer of water from one space to another through pressure is the essential regulatory system of the sunflower via fluid dynamics.
This model is a hybrid of two previous study models that we created for Memo 1. The lights which simulate the sun are wired to an electrical source in order to activate them. The lights are then connected to pumps which are powered by the light source. When the light to the left is activated, the corresponding pump forces water into the bag on the right, and vice versa. This model is another understanding of the movement of potassium ions and water located in the pulvinous bulge.
This model shows how the movement of air is influenced by heat. As each side is heated, in turn bimetallic strips unwind and push panels to squeeze air away from the heat source, just as the sun pushes the sunflower's molecules.
Marbles represent the saturated cells on the back of a sunflower stem. Heat from a light source moves around the structure, melting ice cubes that drain towards the marbles, pushing them to the next level in the opposite direction of the light, just like the cells of a sunflower do.
This model illustrates heat differentiation through thermal expansion and contraction of the air trapped in the bottles. Heat causes the air trapped in the bottles to expand, inflating the balloons. Arranging the bottles in an arc and adding dividing walls allowed for this model to better track the sun. Candles were introduced to speed the process. We lit and extinguished the candles in an order that simulates the path of the sun. In conclusion, the sunflower's pulvinous bulge and heliotropic nature gives it many advantages that help it adapt to its exterior environment. In its adolescent stage, when only the stem is growing, it maneuvers itself to collect the maximum amount of blue light from the sun. Once the stem reaches maturity and its head is formed, chemical reactions enable the flower to follow the sun. This allows for the sunflower to collect the maximum energy to aid in its reproduction, ensuring future generations. In order to prolong its survival, once the head is completely formed, it faces east in order to avoid scorching.